In this episode, we shift from designing secure networks to proving that they behave the way we believe they do, because assumptions about reachability are one of the most common sources of cloud security failure. It is entirely possible to design a network on paper that looks perfectly segmented and tightly controlled, only to discover later that a routing change, a new connection, or a misapplied rule has opened an unintended path. Cloud environments evolve constantly, and with that evolution comes configuration drift that can quietly erode your original design. Validating network design continuously means comparing what should be reachable against what is actually reachable, and treating differences as security-relevant findings rather than minor quirks. Beginners often trust that if they set a rule once, it stays that way. But real environments accumulate changes through new deployments, troubleshooting exceptions, and infrastructure updates. The only reliable way to maintain trust in your segmentation and ingress controls is to test them regularly and deliberately. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. A helpful starting point is distinguishing between intended architecture and effective architecture, because those two concepts are not always the same. Intended architecture is what you think you built, including zones, route boundaries, and access restrictions that reflect your design decisions. Effective architecture is what the network actually permits at any given moment, based on the current combination of routes, gateways, firewalls, and service policies. Investigation questions often arise when these two diverge, such as discovering that a supposedly isolated database is reachable from an unexpected subnet. Beginners sometimes assume that diagrams and documentation reflect reality, but diagrams are snapshots of intent, not guarantees of behavior. Validation closes that gap by testing real connectivity rather than relying on mental models alone. When effective architecture matches intended architecture, you gain confidence that your controls are functioning as expected. Reachability testing is the practical technique used to compare design with reality, and it can be conceptualized without diving into specific tools or commands. At a high level, reachability testing asks whether traffic from a given source can reach a given destination on a given protocol and port. This testing can reveal unintended openness, such as a management interface that is accessible from more subnets than planned, or unintended blockage, such as an application that cannot reach a dependency due to missing routes. Beginners sometimes think reachability testing is only for troubleshooting broken applications, but it is equally important for verifying security boundaries. When you test reachability intentionally, you are validating your segmentation assumptions and confirming that blast radius remains controlled. Treating reachability as a security verification step turns testing into a proactive defense rather than a reactive fix. One powerful mental model is to define expected connectivity matrices, even informally, where you describe which zones should communicate with which other zones and in what ways. For example, you might expect that public entry points can reach application servers, that application servers can reach databases, and that databases cannot reach the internet. These expectations become your baseline for validation. Beginners sometimes feel overwhelmed by the complexity of mapping every possible path, but starting with high-risk zones and critical services provides immediate value. When actual testing reveals a path that contradicts your expectations, you have discovered either a misconfiguration or a misunderstanding. Both deserve attention because they indicate a gap between intention and behavior. Over time, refining this expected connectivity map strengthens your architecture and reduces surprises. Validation is especially important after changes because cloud environments are dynamic and changes are frequent. A new peering connection, a modified route table, or an updated firewall rule can create cascading effects that are not immediately obvious. Beginners often focus on whether the immediate goal of a change was achieved, such as restoring connectivity for a service, and overlook the broader impact. Continuous validation means that after changes are made, you reevaluate key reachability assumptions to ensure no unintended exposure was introduced. This practice reduces the risk of small fixes creating large vulnerabilities. It also supports a culture where change is followed by verification rather than blind trust. When validation becomes routine, your network remains aligned with your security posture even as it evolves. Logging and monitoring complement reachability testing by providing evidence of actual traffic patterns. While reachability tests simulate or probe potential paths, logs reveal real behavior over time. If logs show connections between zones that were not expected to communicate, that discrepancy should trigger investigation. Beginners sometimes assume that if no alerts fired, everything is functioning correctly, but absence of alerts does not guarantee absence of exposure. Correlating logs with expected connectivity patterns strengthens validation by confirming not only what is possible, but also what is occurring. When actual traffic aligns with intended patterns, confidence increases. When deviations appear, they provide early warning of misconfiguration or compromise. Another important aspect of validation involves understanding implicit connectivity that may exist by default. Some cloud networks allow internal routing between subnets automatically unless explicitly restricted. Beginners might assume that separate subnets imply isolation, but routing tables and access rules ultimately determine behavior. Continuous validation ensures that these implicit behaviors are examined rather than assumed safe. It also highlights the importance of testing internal reachability, not just external exposure. Attackers who gain internal footholds rely on these implicit paths to move laterally. By testing from internal perspectives, you gain insight into containment effectiveness. Multi-account and multi-region architectures introduce additional complexity because reachability may cross boundaries that are not immediately visible in a single view. Peering, transit gateways, and hybrid links can create indirect paths that are difficult to track mentally. Beginners may believe that isolation in one account guarantees isolation globally, but cross-account routing can change that assumption. Continuous validation in distributed environments requires holistic visibility and consistent standards. When you test reachability across regions and accounts, you ensure that segmentation principles are preserved everywhere. This prevents isolated design excellence from being undermined by overlooked connections elsewhere. Automated validation can enhance consistency and reduce human error, but even manual conceptual validation remains valuable. Establishing regular review cycles where network connectivity is assessed against documented intent strengthens governance. Beginners sometimes think validation requires complex tooling, but at its core it is about asking structured questions and seeking evidence-based answers. Whether through automated checks or deliberate review, the goal is alignment between design and reality. Treating validation as an ongoing discipline rather than a one-time audit maintains integrity over time. It reinforces the idea that security is a process, not a static achievement. Incident response also benefits from continuous validation because responders need confidence in segmentation boundaries during containment efforts. If a workload is compromised, responders may rely on network isolation to limit impact. If segmentation assumptions are incorrect, containment strategies may fail unexpectedly. Beginners should understand that validation before incidents strengthens response during incidents. Knowing which paths truly exist allows responders to act decisively rather than cautiously. Continuous validation, therefore, contributes to resilience as well as prevention. Documentation and communication support validation by ensuring that intended architecture is clearly articulated and accessible. Without clear documentation, it becomes difficult to determine whether a discovered path represents an error or an intentional design. Beginners should appreciate that architecture documentation is not merely bureaucratic overhead. It is the reference against which validation occurs. When documentation is accurate and updated, discrepancies are easier to identify. When documentation lags behind reality, confusion grows and security weakens. Validating network design continuously by testing intended paths versus actual reachability is ultimately about preserving trust in your architecture. Cloud networks are powerful and flexible, but flexibility introduces the possibility of unintended exposure. By defining expected connectivity, testing regularly, correlating logs with design assumptions, and revisiting reachability after changes, you keep segmentation aligned with intent. For new learners, the central insight is that security is not guaranteed by initial configuration. It is maintained through verification and discipline. When effective architecture consistently matches intended architecture, your network becomes predictable, your defenses become reliable, and your confidence in containment grows stronger over time.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.